Let's start with 2 times 3. Well, we know that's 6, right? But we also know by this point that 2 is equal to root 4, 3 is equal to root 9, and 6 is equal to root 36. Why? Well, we know 2 to the power 2 is equal to 4 because 2 times 2 is 4, so 2 is equal to root 4. 3 to the power 2 is equal to 9, 3 times 3 is 9, so 3 is equal to root 9. And finally, similarly, 6 to the power 2 is equal to 36 because 6 is equal to root 36. Now, none of this stuff should be new to you by now. You know 2 times 3 is equal to 6. And you also know 2 is equal to root 4, 3 is equal to root 9, and 6 is equal to root 36. But let's pay attention to that second row right there. The root 4 times root 9 is equal to root 36, because that's the focus of today's lesson. Notice how that 4 and the 9 have a special relationship with 36 on the right side of the equal sign. Let's look carefully at this root 4 times root 9. In a previous video, I mentioned that the radical kind of acts like a parentheses. What do I mean by that? Well, something really cool happens when we multiply these two together. If we have a root 4 and we have a root 9 and we multiply them together, we can put them all inside the same one large radical. So this 4 and this 9 are in two separate radicals right now. We can combine them into one large one. So that becomes root 4 times 9, which becomes root 36, because we know 4 times 9 is equal to 36. It turns out, we already know this, right? We already know that 2 times 3 is 6, and we know 2 is root 4, 3 is root 9, and 6 is root 36. But it turns out that no matter what's inside the radical, this always works. Whatever is inside the small radicals, you can combine it together into one larger radical, just like how you can do with parentheses. Let's look at some more examples of how this works. So we have root 2 times root 3. Well, we can combine 2 times 3 together to get root 2 times 3. That becomes root 6, because 2 times 3 is equal to 6. And it turns out that if you put this into a calculator, you find 2.449, etc., etc., etc. It's a bunch of random numbers. So it's not a very clean number. Basically what that means is whatever this decimal number is, if you multiply it by another decimal number of the exact same kind, so basically the exact same number, you will get 6. So it's not a really clean number, and as we will see later, these not clean numbers are very different from some of the clean numbers. For example, let's say we had root 2 times root 8. That would give us 2 times 8, and that's 16. So we have root 16 here as a result. But that root 16, as we know, is 4, because 4 times 4 is equal to 16. So already that number is a lot cleaner than that number at the very top. 4 is a lot cleaner than 2.449, etc., etc. As we will find out, this 16 is something called a perfect square because it generates a square root that's very clean. Before I go into this in more detail, because I'm definitely going to talk more about perfect squares in the next video, I do want to go over another example so we can make sure that we are getting this down very clearly. We have, for example, minus root 2 times root 8. And that becomes minus root 2 times 8 because, as I said in the previous video, the negative sign follows all the way down but still stays outside the radical, like as if it was a parentheses. So that negative root 2 times 8 becomes negative root 16, which finally becomes negative 4. As you can see, that negative sign on the very left stayed with this whole radical until it became negative 4 at the very end. So this negative follows the whole way through, which means that you need to be really careful about how you use your signs. And finally, we have this 4 and this negative 4, both of which are clean numbers, which further goes to show that a number inside the radical, the 16, is something called a perfect square, unlike 6, which did not generate a perfect square at the very top. Another type of problem you might see is one like this, where, for example, you have root 6 is equal to root x times root y. Well, this question asks you to use your knowledge of something called factors, which are two numbers you multiply together to get one larger number as a product. So here the larger number, the product is 6, and we need to find two factors of 6, because we know that the two numbers inside the two small radicals can combine together to create 6 underneath the large radical. Well, there's a lot of examples that can work for this. For example, if x equals 2 and y equals 3, that would work. X equals 3, y equals 2 would work as well, because both of them have an x and a y where if you multiply it together, you get 6. Another one is x equals 6, y equals 1. And finally, one last one I can think of is x equals 1, y equals 6. You can use fractions, you can use decimals, whatever you want, as long as x times y eventually equals 6. So as you can see here, this is another type of question that asks you to tackle this concept the other way around. That's a really important type of question in math because sometimes you're not going to be asked to do exactly what you first learned. You have to look at it the other way. This is a question that asks you to do that, which is why these types of questions are really important to test how well you know this concept. Let's move on to the vocabulary. Basically, what are we doing here? We're trying to break up this number that's inside a radical in order to simplify it. Simplifying is really important, as you will see later. For now, just make sure you know that this is all something that's a part of a simplifying process. Make sure you know that you include radicals when you rewrite it as well. For example, root 2 times root 4 is equal to root 8 because 2 times 4 is equal to 8. Do not forget the radicals on top of the 2 and the 4 when you compare it to root 8. Now, given that we already reviewed a little bit in the vocabulary, I'm just going to leave you with this one question. When you write these expressions, when you simplify them, for example, when you write root 2 times root 4 is equal to root 8, are there any ways in which we could simplify these expressions further? Look at that root 4. Is there anything we can do to that root 4 that would make it a little bit more simple than it is right now? I'm going to have you think about this a little bit more as we anticipate the next lesson. For now, we've come a long way already, which is great. I know we can keep it up though, so keep up the good work. See you next time.
Pink, yellow shades just passing by. Oh, I don't wanna say